Hello everyone, now we'll be covering planes. So over here, we have a plane, and what I want to do is describe every single possible point on the plane. So how do I do that? Similar to what we did for a line, is we have O, and we have this line, and we found a positional vector for one of the points on the line. So for planes, I'll find a position vector for one of the points on the line. And then, instead of having one directional vector, we have two directional vectors. Let's say we have this directional vector in green and directional vector in red. Any scalar multiple of these directional vectors can find us any point on this plane. Like let's say we're just going to take a point here. What we do is find that and then plus that. So as long as we have two directional vectors that are non-parallel, and again, the directional vector is any vector that lies on the plane. As long as we have two of these directional vectors that are non-parallel, we can find out the position vector of any point on the plane. So that's what our vector form of the plane is. R, which is the position vector of any point on the plane, A, which is any point on the plane, and here are the two directional vectors. Lambda and mu are just my two parameters where we can have any constant multiple of the directional vector. Now we have two more forms of the plane, but let's focus on the normal vector form first. If you remember, the cross product of any two vectors will give us our normal vector. And this normal vector n is perpendicular to these two vectors over here. And since these two vectors lie on the plane, this also means that our normal vector is perpendicular to the entire plane. This can be visualized like this. What the normal vector form states is that any point on this plane, let's say I have this point, dotted with the normal vector will give me a constant d. So I can have this point A, this point over here, this point over here, this point over here, any of these points dotted with the normal vector will give us the same constant d, no matter which point I use. So I have this formula here, where n is the cross product of the two directional vectors, and d will just be the position vector here. I mean, it can be any point, but since we have the position vector of one point here, we use that point dotted with the normal vector. That is our value of d. And finally, the Cartesian form. First off, since R is any general point on the plane, I can write it as x, y, z. And n, let's say 1, 2, 4, I can write this as 1, 2, 4, and then equals to d. And after I evaluate this dot product, it will look something like this, and this will be just the Cartesian form of the plane. Let's try a question. Find the equation of the plane passing through the points, these 3 points, in Cartesian form. Okay, so we have 3 possible position vectors that we can use. I'm just going to use the first one because why not? But similar to the vector equation of the line, the vector form of the plane can have many solutions. The solution that we are finding is not a unique solution. But again, they all point to the same plane. Now what we need to do is find two directional vectors. So we have this plane over here and we have 3 points, P, Q, and R. What we can do is find PQ and QR. Those are 2 possible directional vectors. I can also find PR, that also works, but I'm just going to find PQ and QR. Vector PQ is just OQ minus OP, and vector OR is just OR minus OQ. Now we have our 1 position vector and 2 possible directional vectors. Now if we want to find the Cartesian form, we first need to find the normal vector. So we need to find the normal vector. And again, the normal vector is the cross product of the 2 directional vectors. And if you remember how to do cross product, the first thing I want to do is take this minus this. And the next thing I want to do is take negative of this plus this. And finally I have this times this minus this times this. So that's just 2 minus 6. And that will get us 1, 2, negative 4. Now if you remember, the normal vector form is just r dot the normal vector, which is 1, 2, negative 4 equals to d. And if we want to find d, we take any one of these points and dot it with 1, 2, negative 4. And remember, r is just x, y, z because it's any point on the plane. So evaluating the dot product, we'll get x plus 2y minus 4z equals to d, and in this case, d is just negative 7. That's the Cartesian form of the plane.